Section 10.5, the ratio and root tests. The purpose of this section is to add two more very important tests to our repertoire for testing for the convergence or divergence of an infinite series. So let's begin with the first one, the ratio test. The ratio test says to assume that the following limit exists. We'll take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, and assuming that that limit exists, we'll call that limit rho. And then the ratio test says if rho is less than 1, then the infinite series, sum of the a sub n's, converges absolutely. On the other hand, if rho is greater than 1, then the sum of the a sub n diverges. Finally, if rho is equal to 1, the test is inconclusive. So this is something that we have to pay attention to with the ratio test. It can be inconclusive. It doesn't necessarily mean that you did anything wrong, but it just might not be the tool that resolves the convergence or divergence for a particular series, and in such a situation you would just need to pivot to a different test. Let's jump in and look at some examples. So example 1, let's determine the convergence or divergence of the sum, n equals 1 to infinity, of 2 to the n over n factorial. So I know that here in the book they use the letter rho, lots of other books use the letter L, and in the root test they're going to use the letter L, so I'll just use L for limit. So let's let L be the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. So the way we get a sub n plus 1 is we just go to the general term a sub n. Remember, this is the a sub n. We're just going to evaluate this when n is equal to n plus 1. So we would get a 2 to the n plus 1 over an n plus 1 quantity factorial, n plus 1 quantity to factorial. And then I'm going to write divided by, we want to divide by a sub n. And a sub n is just what's sitting right here, 2 to the n over n factorial. Don't forget the absolute values. Now everything here is positive, so the absolute values don't matter, but in other examples it very well may matter. So now notice that we have this fraction divided by a fraction, so we'll leave the first fraction alone, we'll invert and multiply. And now notice some very convenient cancellation takes place. Here we have n powers of 2, here we have n plus 1 powers of 2, so with one more power we cancel all n of them, we're left with a 2 to the first power here. This is an n factorial in the numerator and an n plus 1 factorial in the denominator. Remember, n factorial is just n times n minus 1 times n minus 2, and you keep counting down until you finally get to 3, 2, 1, and you stop. So n plus 1 factorial is just going to start at n plus 1 and count down. And notice, once it counts down once, it will get to n and then keep counting down. So all of these are the same. All of these terms are the same. And so we'll just factor the n times n minus 1 all the way down to 2 and 1 here with those same terms here, and we're just left with an n plus 1 without the factorial. And so everything here is also positive, so we can drop the absolute values, and we end up with the limit as n goes to infinity of 2 over n plus 1, and that is going to 0. So since the limit here existed and the limit L was 0, which is less than 1, by the ratio test, the original series converges absolutely. So notice that's a very convenient test. We get absolute convergence in one of the cases of the test. And also notice that the types of functions that work very well in this example, this factorial, by the very nature of the ratio test, and you can see why we call it the ratio test, it's the ratio of the a sub n plus 1 over a sub n. Be sure you get that order correct, otherwise this doesn't make sense. And notice that here the 2 to the nth power function canceled very nicely, and the n factorial and the n plus 1 had a lot of cancellation. So those are telltale signs of when the ratio test has a good chance at succeeding. Notice that in the test, when they say that the limit being 1, the test is inconclusive, or you can think it's indeterminate, what that just means is that in different examples, you can get convergence for some examples with the limit being 1 and divergence in others. As a quick example, I don't show the details here, but you can check for yourself. If you were to do the ratio test on this series, which is obviously divergent because the nth term does not go to 0. These terms are all getting bigger and you're adding up infinitely many of them, so this is going to infinity. If you check it with the ratio test, you will get an L of 1, and this infinite series diverges. On the other hand, this infinite series also has an L of 1. but it's a p-series with p equals 2, so it converges. This is just to showcase that you have two completely different examples. They both have an L of 1. One converges and one diverges. So it does mean that when you get that L equals 1, you need to pivot to a different test. So let's look at example 2. How about the sum from n equals 2 to infinity of 1 over ln of n? Does it converge or diverge? We'll use the ratio test, so we'll let L be the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. So we'll just write the limit of that absolute value. For the a sub n plus 1, we'll just take the general term. Where we see an n, we'll put an n plus 1. Divided by, we'll just write the general term a n here. Everything here is positive. N's greater than or equal to 2, so the natural log function is positive. Everything here is positive, so we're free to drop the absolute values. We have a fraction divided by a fraction. Notice this is always the way it will be with a ratio test. And so there's always going to be a fraction or a ratio involved. And so here we just leave the first fraction alone. We invert and multiply. And now we could use properties of logs to deduce this limit, but we could also notice that this is an infinity over infinity indeterminate form. And so by an application of L'Hopital's rule, the derivative of the top is 1 over n. The derivative of the bottom is 1 over n plus 1. After a little algebraic rearrangement, this is, again, either you could think of it as another infinity over infinity indeterminate form, and we use L'Hopital's rule, or you could use your knowledge from calculus that the degree of the numerator is the same as the degree of the denominator, so the limit is the ratio of the leading coefficient, so this goes to 1. But that theorem came from L'Hopital's rule. So we're really just using L'Hopital's rule again, and here we get a limit of 1, and since the limit here is 1, the ratio test is inconclusive. So it doesn't necessarily mean that we did anything wrong, it's just the ratio test is not the test to use for this one. Notice if you just were to pivot to a direct comparison that you get a straightforward result. Since n is greater than 2, we know that the natural log function is positive, and the natural log function is always less than n, because the natural log function grows slower than every power function. And so if we reciprocate these, we get that 1 over n is less than 1 over the ln of n, and everything's still positive. And so the sum of the 1 over n's is less than or equal to the sum of the 1 over ln of n's. And when we do that, we see that the series that we had is actually, this should be a 2. We'll fix that. And so we see that this is a harmonic series and it diverges. And so the series that we have is actually larger than something that is known to diverge. And so by the direct comparison test, the given series diverges. So notice even when the ratio test was inconclusive, we just pivoted to a different test and still were able to determine the convergence or divergence. Okay, let's look at the next test, the so-called root test. And the root test says to assume that the following limit exists: the limit as n goes to infinity of the nth root of the absolute value of the a sub n's, and we'll call that limit L. And number 1, if L is less than 1, then the sum of the a sub n converges absolutely. Number 2, if L is greater than 1, then the sum of the a sub n diverges. And number 3, if L is equal to 1, then the test is inconclusive and you need to pivot to a different test. Let's look at example 3. Let's determine the convergence or divergence of the sum from n equals 1 to infinity of n over 3n minus 1, all raised to the nth power. So in the spirit of the root test, let's let L be the limit as n goes to infinity of the nth root of the absolute value of the a sub n's. This entire thing is the general a sub n. So we are taking the limit as n goes to infinity of the nth root of the absolute value of all of this. And now notice, because we had an nth power, and first everything here is positive, so we can do without the absolute values, although that might not be the case in every example. But notice that when we do away with the absolute values, we're taking the nth root of something raised to the nth power. And this is a telltale sign to use the root test. When you see something with a variable power, especially an nth power involved in it, then you want to try to use the root test. So notice this gives us a very nice cancellation. We're taking the nth root of an nth power. So we just, since everything here is positive, we just get n over 3n minus 1. You could either do that using algebra, calculus, L'Hopital's rule. This limit goes to 1/3. Since L, the limit is 1/3 is less than 1, then by the root test, the given series converges absolutely. Okay, let's look at another example. Does the sum from n equals 1 to infinity of minus 1 to the n minus 1 over ln of n plus 1, the whole thing to the nth power, does that converge or diverge? Well, I tried to give an example here where we're not just having strictly positive series, and this is an alternating series, but I did want to choose something where the absolute values make a difference. And so here we'll take L to be the limit as n goes to infinity of the nth root of the absolute value of the a sub n's. And what's motivating me to use the root test here isn't this nth power, but rather the nth power that I see here. And so when we substitute in what the general nth term is, we get this with absolute values. Now notice when we apply these absolute values, this is just a minus 1 to a power. So when we take the absolute value, we're just going to get a 1. Notice all of this is already positive. So when we take the absolute value, it doesn't make any change. So we can just drop the absolute values. But the absolute values acting on that minus 1 to a power was very important. And now notice we're taking the nth root of 1 over this stuff to the nth power. Well, that means we can take the nth root of the numerator, which is 1. The nth root of the denominator here is ln of n plus 1. And now this is a limit that we can quickly resolve. The numerator is 1. The denominator is getting larger and larger, so this is going to 0. 0 is less than 1, so by the root test, the series converges absolutely. Okay, so those are two very important tests that we've added to our repertoire, but also in this section, you'll see in the second half of the homework that they're taking all of the tests that we've learned in Chapter 10, and they're just going to mix and match them where they don't tell you what test to use and see if you can discern which test to use based on the given look of the series that you have. So I wanted to give some overall strategies. These are not airtight rules to go by, but they're more pointers or things to think about when you're assessing a series and you're trying to figure out which test to use. So just some overall strategies. Number one, the test for divergence should always be used right off the bat. It can be applied very quickly. Remember the test for divergence, you can go back and look at the statement, the formal statements of every one of these. I'm not trying to restate formally what the hypotheses and the way you draw the conclusion from them, but rather how you know which test to reach for and what it may accomplish or may not accomplish. So the test for divergence just says that if the nth term does not go to 0, then the sum of the a sub n must diverge. So this quickly determines if a given infinite series has any hope of converging. If the nth term does not go to 0, the series is going to diverge, and you can just stop there. So always kind of quickly mentally check for the test for divergence right when you're given a series. Now the next category is what if you have positive series? You have to remember these tools, the integral test, the direct comparison test, and the limit comparison test, they only applied for positive series. That's very important. The integral test, one thing to look at when you're given an infinite series and it's a positive series and you think you might want to use the integral test is you just want to quickly look at it and say, does that look like something that's going to be amenable to integrating it? So for example, if it had n factorials or something like that in it, you wouldn't even think of integrating it. If it's too overly complicated and it doesn't look like a U substitution or parts or partial fractions or some integration technique will quickly integrate the associated improper integral, then you probably want to move on to something else. Secondly, the direct comparison test is, remember, you have to have a useful, true comparison. And if one of those isn't immediate, normally when you have terms that are added or subtracted together, you can remove a term in order to get the inequality running in a certain direction. Hopefully it's in a useful direction, but that is sort of the art form of the direct comparison test. The art form of the integral test is you have to be able to spot that you can integrate it and actually execute the integral. And the art form of the direct comparison test is you have to come up with a direct comparison that's both true and useful. The limit comparison test doesn't require for you to have an inequality, so I think that makes it a little easier to use, but you do need to come up with the b sub n. And one thing that we showed you was using a dominant term analysis is a very common way. Doesn't always work, but it's a very common way to generate the b sub n. So there's the art form. Where is the b? How are you going to come up with the b sub n? And then another tip is you can always try your b sub n to be 1 over n or 1 over n squared. Usually if you suspect that the series diverges, you can try 1 over n. If you suspect that it converges, you can try 1 over n squared. That is certainly no guarantee that those will work, but if you can't come up with anything else and a dominant term analysis doesn't get you anywhere, then those are always things that you can try. Now, the ratio and the root test, they're always in play. They don't require that the series are positive, but they're certainly applicable to positive series, so remember that they're always in play. And the third category is, what if you have not necessarily positive series? I don't want to say alternating because they might not be alternating, but if you have a series that doesn't have all positive terms in it, you should certainly check to see if it's alternating. Then you could use the alternating series test, of course. You have to check the hypotheses. So it has to be alternating or you wouldn't even consider using that test. The ratio and the root test don't really care whether the terms are positive or negative because they're going to have absolute values in them. So they are another very useful test to use for not necessarily positive series. In terms of using the ratio test, you can probably tell from the examples, and you'll get a better feel for this as you work through the homework, is the ratio test usually works very nicely when the general term is of a form that simplifies nicely over multiplication and division. Things like n factorials, exponential functions, sometimes power functions, depending on the type of combination that you have. But that really is something that a ratio test has a chance to shine on. And finally, for a root test, I think the dead giveaway for a root test is when you see an nth power, not necessarily the nth power that occurs like in an alternating series, but as we saw in our previous examples, where we had some something that wasn't minus 1 to an nth power, some other part that had an nth power in it, that really sort of screams for the root test and would be very messy to try with something else. So these are just some general tips to keep in mind when you're just confronted with a random series and you're trying to figure out which test to use. It's a lot like when we did integration and you had to figure out which technique of integration to use. You have to kind of see what are the pros and cons and what are the features of different techniques so that you know which one to reach for. The last thing I would say is when you are going to mix and match all of these different tests for convergence and divergence, you absolutely have to have certain series in your repertoire that you know about their convergence and divergence because you may need to use them along the way. The P series are a famous batch of series that, remember, they look like this. And you can go and look back at the notes. P series converge when P is greater than 1 and diverge when P is less than or equal to 1. Two famous P series, or they come from P series, is when P equals 1. You get the harmonic series. This is a classical series that diverges. And then similar, but it's not exactly in this form, this is an alternating harmonic series. The alternating harmonic series converges. So these are two very, very important P series to keep in mind. And then always geometric series, remember what they look like. Remember that geometric series converges when the geometric ratio R has an absolute value strictly less than 1 and it diverges otherwise. But these are definitely series that you should have in your repertoire and be ready, willing, and able to use them in a comparison or along the way with any of these other tests as you confront them.